Welcome back. Today we will talk about solar concentration and solar thermal energy conversion. Using mirrors, concentrators is not very new. It has been applied since a long time. Even there are histories that in ancient Greece, the Greek army used police shields to set the Roman fleet on fire about 2000 years ago. But this is a bit later. This is in Paris at the World Exhibition in 1889. And you see here a parabolic mirror, and the light concentrates in the middle and heats up water. This is converted to steam and drives a steam engine, and the steam engine drives a printing press. This is a principle. So you have here the effective area of solar direct irradiance and the according irradiance value in watt per square meter. This is then concentrated on a smaller area, and accordingly you can achieve higher temperatures then. You don't have to have a real parabolic mirror. You can also split it up into smaller mirrors which are of the same reflecting angle, and you can make a so-called tower power plant as shown here. Or you can make, instead of a parabolic mirror, you can use a parabolic truck, and then you have not a focus point but a focus line, as you see here, and you can also split that area up in different stripes. Here you see the achievable temperature and the collector efficiency. So you have here for C1 is no concentration at all. You see that the maximum absorber temperature is in the vicinity of 170 degrees Celsius. The efficiency is 0. That means the so-called still stand temperature. The water you're pushing through there is standing still. Therefore, if you don't take any power off, the efficiency is going to 0. Here you have the highest efficiency at the lowest temperature because the throughput is very high and the time to heat up the water is very short. On the other hand, you don't have a lot of thermal losses due to the minimum increase in temperature. Here you see the different concentration ratio. For example, here C to 10 times concentration, you can achieve temperature a little bit above 500 degrees Celsius and so on. The maximum here is shown as 1000. Here in the logarithmic presentation, you see here the maximum achievable temperature, and you see here the maximum that could be achieved is 5707 Kelvin. That's exactly the surface temperature of the sun, and the temperature doesn't go higher due to the second law of thermodynamics, which say you cannot achieve a higher temperature going out from a smaller temperature, and therefore the maximum is the same temperature as you would have on the surface of the sun. Here you see a construction from the 50s in southern France. During that time, France didn't have the nuclear policy yet, so they were quite interested in solar energy. And this is a 16 megawatt power plant, and you have a double reflection. So you have first you have 63 plane mirrors which direct the sun's irradiance onto a building, which is quite high, 40 meters here, and then you have a real big mirror here which concentrates which concentrates the incoming irradiance on a focus point. The concentration factor is 16,000. Then you have a power density of 1.6 kilowatt per square centimeters. The achievable temperature is 3000 degrees Celsius. The efficiency, the optical efficiency, is 60%. This is our modern construction from the 80s in the United States in the Mojave Desert. It is called SEGS, Solar Energy Generating Systems. This is set up by parabolic trucks, and you have here, as I mentioned, a focus line. This tube is usually black, but due to the high concentration of solar irradiance, the little reflectance here makes it appear to be black, but this is only reflected sunlight here on the black pipe. You have here an oil which goes through that pipes, and via a heat exchanger here it's converted into steam, and the steam drive some steam turbines, and these are coupled to electrical generators, and in total you have electrical power output of 354 megawatts. The mirror area is 2.6 square kilometers. The electrical energy costs are 10 euro cent per kilowatt hour. This is relatively expensive compared to nowadays photovoltaic power plants. In such conditions as the Mojave Desert, you can generate electricity in the vicinity of 2 cents per kilowatt hour. Here you have the energy flow at a parabolic mirror. So you have the reflector, the incoming irradiance, you have some losses at the reflections, then you have also some losses on the way from the mirror to the absorber, not very much, but then you have some losses, as you saw, by the reflection of the surface, the glass tube here around the absorber, and then you have the absorber also with some losses. Then you have here the final absorption point, and with a certain temperature. Then you have losses by thermal radiation or by convective heat transfer. Another way to concentrate this is via Fresnel lenses. These are kind of flat lenses, and this is an example. In general, you have always to track the sun if you use concentrators, because otherwise the focus point wouldn't fit to your absorber, and therefore you always need a tracking device which follows the sun. Let's take a look into the scheme of conversion. So this is a representation of the energy flows occurring at a solar thermal energy converter. So you have here on the top, you have the incoming irradiance. Then some part of that irradiance is being reflected. The blue part is our converter. You need some energy to produce it, so they're called gray energy. And then you have some parts may be transmitted if you have another opaque transformer here, and most of it is converted into heat. This heat is either stored or dissipated via convection or radiation or conduction, or you have just usually your useful energy. You get it away with you transport it via a water flow. Additionally, we put here for the photovoltaic devices the energy flow taken by photovoltaic energy conversion. This is a solar flat plate collector. So you usually have a cover glass with some absorption. Then you have a reflection according to the Fresnel equation. This is usually at a glass air interface, about 4% at each interface. If you have two interfaces here, it's about 8% in total reflection, plus 2% of absorption inside the glass. And then you have the same issue at the absorber. You have some reflection at the absorber. Then you have the thermal energy here. And you have losses, thermal losses, then the natural convection in the vicinity of 13%, and the thermal radiation, because also the absorber is a black body which has a temperature which is above the ambient temperature, so it's emitting thermal radiation. This is a bit reduced due to the cover glass. Usually glass is transparent in the visible range, but not transparent in the infrared range, where the thermal emission of the absorber takes place. And also you don't have a perfect insulation layer, so you have also some losses due to thermal conduction. At the end, typically you have an overall efficiency in the vicinity of 60%. Here you see the conversion efficiency at different irradiance levels. So usually the standard test conditions for photovoltaics is 1000 watt per square meter. At solar thermal systems is 800 watt per square meter. You see here the achievable temperature difference and the conversion efficiency. So you see here at temperature difference of 70 degrees, you have a conversion efficiency of about 50%. divided the losses of thermal losses. These thermal losses increase with increasing temperature difference. The conduction part is linear with temperature difference, but the thermal radiation part increases with a power of 4 by temperature. Plus you have optical losses, they're already mentioned here, just the losses on the glass interface and also reflection losses on the surface of the absorber. So you see here at 200 watt per square meter, you don't achieve any higher temperature, more than 42 degrees or so. So if you need a temperature difference with 50 degrees Celsius, that's not possible anymore with a conventional flat plate collector. If you change the design of the collector a little bit, you may achieve higher temperature. For example, here, this red line, it shows a vacuum tube collector. That means we have a vacuum. So if you have a vacuum, natural convection cannot occur anymore because this requires air. Thermal radiation still occurs, sure, because even a vacuum is transparent for thermal radiation. The glass must be a bit thicker, so you will have more absorption losses. And often this is designed as a tube to cover the higher pressure. Therefore the reflection losses are also higher. So you see here, this is the relative conversion efficiency here. This is at 800 watt per square meter. So you can achieve temperatures above 200 temperature differences, above 200 kelvins. And you still have a conversion efficiency of, how much is it, 11% or so. And if you go down, we talked about 70 degrees. So you really have a high conversion efficiency in the vicinity of 68%. Here, this was the conventional flat plate collector consisting of one glass. First, we discuss about the non-selective surface. So this is this curve. And you can improve that by putting two glasses, so you have this curve then. But as you see here, while two glasses, you have here the optical losses. The optical losses are higher then, and so you have small temperature differences. You have, for the first part, a lower conversion efficiency. Even a totally uncovered absorber, just as a black tube in the sun, is preferable at lower temperature difference. So this may be enough, for example, to heat up a swimming pool or so, if you need just an increase of temperature in the vicinity of 5 Kelvin or so. Now come to this part, the differences between selective and non-selective. You see there's a big improvement, while you don't have an increase in optical losses as you do if you use a two-glass collector. Here you see the functioning of a selective collector. So first, this is a logarithmic scale, so this looks a bit different. You have here the black body radiation of the sun's surface, looks like this, with the maximum at 0.5 micrometer of 550 nanometers. Then you have a non-selective absorber here, and it absorbs everything here from the sun. And you have here the black body radiation at 350 Kelvin. That's the black body radiation of the thermal absorber here. And there is a law that says that the emission is equal to the absorption. So alpha is equal to epsilon. That means you have a good absorption here, which is required. You want that. But usually you don't want high emission here at the black body radiation. And non-selective absorber doesn't care about this. So here's also here a good absorption as well as a good emission here. This is then not preferable if you have a selective absorber. It's very capable to absorb in the spectrum of the sun, but absorbs and emits less in this frequency range of this wavelength in the vicinity of 10 micrometers. There it doesn't absorb as well, it doesn't emit anymore, and therefore the losses by thermal radiation are reduced. And this you can see here. So here you have lower thermal losses here, and therefore you can achieve higher temperature differences. Or if you go to the same temperature differences, look here, for example, at 75 Kelvin temperature difference, you have at a non-selective absorber, you would only have a conversion efficiency of 10%, while you have a conversion efficiency in the vicinity of 40% if you use a selective absorber. So now we come to the systems after we talked a while of the collector. So this is our collector. The most simplest system is the so-called Thermosyphon system. That means you have a source of cold water here flowing into the collector. The water heats up, and due to the buoyancy, the water flows automatically upwards here because the density of the water is getting lower at higher temperature, and it goes into a second storage, or in this case you have a single storage with stratification inside it. So the hotter part is on the top and the colder part is on the lower part, and then the water flows automatically and heats up the whole storage tank. While the buoyancy is quite low, it only works up to a certain height, which is only about a half a meter. Also, you have to take care you don't make any curve with the tubes and so on. So this is in principle very simple, but sometimes you see a lot of systems which don't work because either the height is too high or too many curves in the tubing. The best would be if the storage would be very close to the collector. There's even some integrated solutions which do that, and so you make sure that the tubing and the height is adequate. Here you see some examples. System made in Turkey here. You have here the storage, 160 liters, and a solar collector with 2.3 square meters, and the water flows in here, goes up here, and then it's stored in the upper part of the storage. Here some other manufacturers. Solar Heart is an Australian brand. This is Bachiroca. This is a Portuguese brand, but in principle they look pretty much the same. This is also an integrated system of a Brazilian producer. Unfortunately, you cannot apply those systems in Germany, while outdoor temperature can go below zero, and that would mean if you would have a Thermosyphon system that the collector would break because it's the same water that goes here inside the collector which you take off then, and if the water is freezing, then it would damage your collector. So you use a two-circle system in Central Europe. So you have here a fluid which is not water but a mixture of water and glycol, for example, which doesn't freeze down to temperatures of minus 20-25 degrees. Then you have a heat exchanger. This heat exchanger inhibits the use of this buoyancy drive, so you have to have an additional pump here. This pump has to be controlled. Usually it's done by a temperature sensor, so when the temperature is high enough it starts to pump. Also it avoids that during night, for example, the pump is working and the temperature is low and then the pump doesn't work. Then you have the hot water storage here, just it's pure water, then just heated up by the heat exchanger, so there's no direct contact of the media from the collector to the hot water storage. Then you have another circuit to give additional heat by a conventional heater, and then you can take off here the heated water and it's feeded again with cold water. Here we should see a movie about a simulation package to calculate such systems, solar thermal systems. So here an interface where you can choose the different components. To define the different components, as you saw, there are different collector types, different areas, different pipe sizes and length and so on. Here you see just the definition page of the collector array and the water tank. How good is insulation? How's the stratification? How big is this? And what's the hot water consumption? What temperature? What volume? And then you can carry out a simulation for a day, or for a year, or for a lifetime. So it simulates really the physics, the mass flow, and temperature, and so on. And it uses steps between 1 and 6 minutes. So you see here it's heating up here. So here the stratification takes place. You have a hot part here and the cold part here. And you have here, finally now all the tank is filled up with warm water. You can take off here on the top. Here you see the additional heater here, as I mentioned already in the other scheme. Simulation goes on. It's getting night. And so you still take off hot water, and then the volume of the hot water is decreasing and it's filled up with cold water. Here you have additional heater you saw just, which supplements a little bit of the hot water, or which adds some heat to the hot water. Final part is the presentation of the results and the financial analysis components, and it calculates the overall efficiencies, the costs, and so the cost-benefit ratios. Here you see the solar contribution or solar coverage. So you see in summer you have almost 100% of solar energy use. You can also put an energy balance there and see where the bottlenecks are. Maybe you can even exchange some components in order to improve overall efficiency and overall performance. Yes, you can also compare two different configurations in terms of costs and efficiencies. As of all, database, you have some manufacturers and they give you the data of their products, and you don't have to put them in manually. Also, air collector systems, okay, that's quite exotic because you need a lot of air to transport heat. But if you have the opportunity, you may do that. You have the auxiliary heating, as we saw just from conventional oil or gas burner here. Here the two-stage tanks. So you can now select the location. It automatically looks up the according irradiance values and the distribution of irradiance during a year, and then you can carry out a simulation. So this is now the configuration of a larger system as we've seen in the desert of Arizona, the SEGS system. So you have here the solar truck collector field, the storage. Usually you have water, but in this case for the Arizona desert it was oil, which could be heated up to 300 degrees Celsius without evaporating. Then if you need it, you put in water via a heat exchanger. Then you create steam when you need it, because the steam pipes are much more expensive than just the conventional fluid pipes. And then if you need it, sometimes even in the desert, there are some clouds, you have an additional heater. Or if there's some unexpected loads and you need to produce more power together, you put that steam through a turbine. Connected to that, there is a generator, and you power homes then. Then the water is condensed in a condenser and the cycle starts again. Due to the additional heater and the storage of the hot oil, you have 100% power availability. It's an additional value. If you have only photovoltaics, then you only have power when the sun is shining. Here you have 100% availability. This is a Convective Airstream power plant by Professor Schleich in Stuttgart. So you cover a large area of land. The land is heating up. This coverage is transparent, for example, by glass or by transparent foil. And then the hot air is going up, and it can only go through a chimney and can reach quite high wind speeds in that chimney, and you can profit from that high wind speed by attaching a wind turbine to it. It was planned first for 50 kilowatts. It showed very good results, and it was extended. There were plannings in the megawatt range, but finally, due to the steep cost decrease of photovoltaic power plants, the whole project stopped during the last year. Another project to profit from the high availability of sunshine in northern Africa and make either direct electricity via photovoltaics. This was some years ago. There was still 4 to 5 cents per kilowatt. As I told you, we are now below 2 cents per kilowatt hour in desert areas. This is much cheaper. Solar thermal energy, the only advantage is stored, but usually it's more expensive than the photovoltaic energy. Also can think about some wind power, which produce in this area is southern Morocco in the vicinity of 2 to 3 cents per kilowatt hour. Then we transport that energy into Central Europe via different transmission lines. Next lecture we will discuss about photovoltaic energy conversion. Thank you very much.